Hello, welcome back to the Open Polkadot Bootcamp. In the last video, we're gonna learn about the path of the parent block. I break down very thoroughly how the parent block gonna be correlate from the parent to the relay change and how it can be added to the shared distributed ledgers of the relay change. Today we're gonna learn how that you can build a parent change from a solo change, how you can configure add a new palette and also register a new parent change on the relation network. To recap a bit on what we already learned and how we're gonna move from what we learned to the set of libraries that allow us to build a parent change. So we learned that frame is the framework used to create a substrate-based application logic, aka the runtimes, and the substrate is the base blockchain framework used to power the Polkadot SDK. It is a full toolkit to create a sovereign blockchain, including but not limited to those who connect to Polkadot as a parent. So you can see right here that you have the frame as the top of the pyramid, and then the substrate gonna be like the lower bottoms. And frame and substrate combined together allow you to build a sovereign blockchain. However, to connect to Polkadot, you need more than that. The first one will be Cumulus. So Cumulus is what we're gonna learn today. Cumulus transforms the frame-based runtime into the Polkadot compatible parent runtime and substrate-based node into the Polkadot parent compatible node. We can also call Cumulus as a parent SDK, a software development kit to build a sovereign blockchain to a parent. Then we have XCMs, short for cross consensus message. It's the primary format that is used for communication between the parent, but it's intended to be extensible to other use cases as well. And we're gonna learn about XCMs in the section 10 that we have 3 to 4 different videos about XCMs. To find any information related to Cumulus, you can possibly go to Polkadot SDK and then find Cumulus. There's a folder in the Polkadot SDK, and as we already learned, Polkadot SDK is a monolith repository, so everything is gonna be under the Polkadot SDK. Cumulus can also be understood as a parent SDK, SDK that allow you to build a parent. And Cumulus contain a set of tools for writing substrate-based Polkadot parent, referred to in the included overview of the architectural details. You can also see the overview of the Cumulus runtime and also the node right here. And also there's sections on the substrate official documentation about connect to a relay change, how to guide for a guided workflow of using these tools to build a parent. So it's easy to write blockchain using substrate, and the overhead of writing blockchain distribution, peer-to-peer, database and synchronization layer should be just as low. So this project aims to make it easy to write blockchain for Polkadot by leveraging the power of substrate. For the consensus layer, Cumulus contains the parent consensus. It's a consensus engine for substrate that follow a Polkadot relay change. This will run a Polkadot node internally and dictate to the client and synchronization algorithms which chain to follow, finalize, and treat at best. For the collator, as we already learned in the path parent block, collator is responsible for participate in the collation process. That is gathering the transactions and also the parent block from the substrate blockchain that connect to the relay change, and then collate that to the parent validator set for the purpose of block inclusion. So a parent collator for the parent is implemented using this package, Polkadot parent binary. And if you already take a look at the Omni node that I mentioned before, Polkadot parent right here is also used in the Omni node binary as well. You may run Polkadot parent locally after building it or using of the container option. So for the relation interactions, to operate a parent node, a connection to the corresponding relation is necessary. This can be achieved in one of the three ways. So run a full relation node with the parent node, connect to an external relation node for the WebSocket RPC, run a light client for the relation. For the in-process relation node, which is the relation node that you run internally. So if an external relation node is not specified default behavior, then a full relation node is bound within the process. So this node had all the typical component of regular Polkadot node, and will have a fully synced with the relation node to work. An example command, we have Polkadot parent. We specify the chain spec of the parent and also the relation spec. For the external relation node, then an external relation node is connected via the WebSocket RPC by using the relation RPC URLs. And parent node using this feature won't have to fully sync with the relation node to work, but in general they will use fewer system resources. Note that at this time, any partition node using this feature will still spawn a significantly cut down relation node in process. Even though they lack the majority of normal progressive system, they will still need to connect directly to the relation network. And to use the external relation node, then you can specify with the Polkadot partition as our binary, then specify the change of the partition spec. Then you use the feature that we already mentioned, like relation your RPC URL, and specify the RPC of the relation. Then also we require the spec of the relation as well, using the relation like client instead of the in-process and the external relation. So an internal relation like client provides a fast and lightweight approach for connecting to the relation network. It provides relation notification and facilitate runtime call to specify which chain the like client should connect to. User needs to supply a relation spec as part of the relation argument. The command would be like the Polkadot per change. You specify the spec again, but here you use a different feature flag called a relation like client. And then you also require the spec of the relation. And in that way, it's gonna spawn a like client small dot and that connect to that relation. And that is the overall of how that you can use the Polkadot partition to launch the collator node and connect to a different kind of relation like in process, external, and like client. Over here, we also have ZombieNet installation setup the Cumulus, and also the ZombieNet. We're gonna learn about ZombieNet later when we visit the POP CUI. In the process of building a branch, there are different stages. The first one would involve the Cumulus library that you add to your runtime and so your node to turn your runtime to a partition runtime and also to turn your node to a partition node. So as you can see right here, the left diagrams, the left visualizations is our blockchain node that has the runtime doesn't configure with any Cumulus libraries. And this one simply just have some libraries that already know like palette order, palette ramper for black finality and block productions. Then you have some custom logic palette, like palette community, palette NFT, something like that. With our solution node right now, it's just a sovereign blockchain solution node. Then if you want to convert your blockchain node into a partition node, you need to change and also add the new libraries to the runtime and also to the solution node. Here I got listed some of the key libraries on the runtime side. You have palette ECMs, Cumulus palette partition system, Cumulus palette over extension, Cumulus palette ECMs, palette collator selections, and Cumulus palette ECMPQ. Here we have palette ECM, palette ECMPQ, and Cumulus palette ECMs. It's not related to the parachange, but it's related to the ECM functionality of the parachange. But the palette ECM is basically configure the palette, configure the ECM executor for your runtime. We're gonna learn that in the section 10 as well. And Cumulus palette ECMs is extending the functionality of your parachange to accept the palette ECMs. And you have the Cumulus palette ECMPQ. It's basically adding this SCMP the message queue for the SCMP message to your parachange. Then you have Cumulus and the palette partition system. This one turn your runtime into a partition system. It has core functionality of the parachange. And palette over extension, extending the functionality of extending the features of block productions of your runtime. So this one is related to the palette over. So that's the reason why it's called palette over extension. And palette collator selections. This one is required for the collator selection, very obvious. I also break down some of the steps required for this section 7 and section 8. That's how you can configure the substrate runtime in the node and also repair a local relation. Then you already have a local relation. We're gonna connect a partition to a local relation. Disclaimer: we actually don't repair a local relation, but we just go through some of the process of how to repair a local relation, because actually to build a local relation need at least a few, maybe 50 gigabyte on your machines to compile them in the Polkadot SDK. And meanwhile my machine right now is not doesn't have much capacity like that. to repair our local relations. So we're gonna just go through some of the process and see how it looks like at the end. Now we go back to the Cumulus and let's walk through the high-level documentation of Cumulus and what it provides to us before we go to the real code. So Cumulus, like each subtree blockchain provide runtime, and the runtime is state transition function of the blockchain. Cumulus provide interfaces and extension to convert the subtree frame runtime into a parent runtime. So Polkadot expects each runtime exposes an interface for validating a parent state transition functions, and also provide interfaces for the parent to send and receive messages of other parent. This is related to the XCMP queue that we just mentioned, but we're gonna learn about that later. So to convert a subtree runtime into a parent runtime, the following code needs to be added to the runtime. Cumulus over palette parent system register validate block executed. Before we dive deeper into the overview, we're gonna let's take a look at this Cumulus documentation. We don't want to try to cover anything here, but just try to visit the Cumulus palette parent system and understand like why do we need that and why we need that register validate block. So a Cumulus palette parent system is a base palette for Cumulus base parent. So this palette handle low-level details of being a parent. Irresponsible include injections of the parent validation data, ingestion and dispatch of incoming downward and lateral messages, coordinating upgrade with the relay change, and communications of the parent output, such as like send message, signaling an upgrade, etc. So user must ensure that they register this palette as an inherent provider. So like this palette is required for any like kind of parent. And for the register validate block, so this register the validate block functions that is used by the parent to validate block on the validators. For the register validate block, what it have is accept the runtime, the block executor, and the check inherent. Now we understand like why do we need this live code. Then so like a few explanation here. So this macro code expect the block and the executive type. It generates the validate block function that is expected by the Polkadot to validate the state transitions. So when compiling a runtime that uses Cumulus, a WebAssembly binary is generated that contains the full code of the parent runtime plus the validate block functionality. So this binary is required to register a parent on the relay change. When the parent validators call the validate block functions, it passes the POV block when they learn the POV's brute validate block to solve the validations. So the POV gonna be sent to the PVF for the validation function, and this is the PVF that we're talking about. And the parent header of the parent is stored on the relay change. So from the POV block witness data, the Cumulus later reconstruct the partial join. This partial join is used as the storage while executing the block. So Cumulus also redirect all storage related functions to use the witness data storage. After the setup is done, Cumulus call execute block with the transaction and the header stored in the POV block. On success, the new parent header is returned as part of the validate block function block result. So simply speaking, the validate block function is gonna gather necessary informations to recompute from the POV block witness data, recompute the join, and to see the state transitions of the parent. So that in that way it can validate the state transitions of the parent is correct or not. Now you may notice in the guidebook I also attach a repository called parent from scratch, and this basically an exercise that allow you to build a parent to configure the runtime following this step. As we already talked about that this runtime configurations is only one stage of building a parent and connect to the relay change. For the parent need to work, we're gonna visit that in the later sections about connect and also about connect to our local relay change, and also how to launch a local network with the POP CLI. So in this here, you see in the build parent from scratch, you can find there's a lot of to-dos, and if you use the VS Code, then also an extension that allow you to view all the to-dos that we have here. If you go to the runtimes, you can find there's a lot of to-dos. Here, yeah, you can find there's a lot of to-dos in the runtimes. And in this runtime, I also explain why we need those to do and what we should do. For example, here you have configure the size extensions for storage weight reclaim for Cumulus parachute block, or we also have the another one called like configure the palette for like palette ECM narrations. So these like you can follow it step by step. You don't have to configure everything for the ECMs, but maybe like first focus on like the parachains only. For example, as we already learned, like for the runtime, the most important part is the palette registry. So this endpoint that allow you to register all the palette, and we have like here like also like separate which one is the ECM helpers like ECM PQ, ECM module, Cumulus ECM queue, message queue, and we have like collator selections, Cumulus palette or extensions, and configure the pattern info and parachain system. And for the parachain, we only have to work on the configure the pattern system, configure pattern info, configure the collator selections, and Cumulus palette or extensions. For the ECM helper, we don't have to care about that. Then like you're gonna register validate block when you already like configure the pattern system of this palette. So we're gonna take a look at the cargo time. So in the cargo time, you can find like there's a lot of packages that already be like coming out. For example, you have like the Polkadot like here like you have like a set of libraries from Cumulus. We are already disable, and your role is to like enable these dependency and use them in the runtime and solid node. So you, for example, you have like the Cumulus, like these are for the client for the node. We don't have to care about that. We only care about the runtime. For the runtime, you have the palette or extension. As we already learned, this is extending the functionality of the order to support the parachain, that allowing you like to combine with the collator selections, and then gonna like collate the block to the relay change. Then you have the Cumulus like palette parachain system. This for like providing the validate functions, handling all the injections and the word messages that we already learned. Also, like you have like ECMP and ECMPQ, ECM and ECMPQ. This one is for ECM, so don't need to care about that. And you have like the parachain info. The parachain info is a very simple palette that basically like register the ID for your parachain. So here like we'll take a look at the code of the parachain info, and this parachain info, as you see, is also like one of the palette. And this palette, the structure is very simple. You have nothing in the hook, nothing in the config. So for the Genesis config, you have a parachain ID, and you also have one storage called parachain ID. So it's basically like it's gonna like register the ID for the parachain on the Genesis config of the blockchain. We can provide the parachain ID on the config on the build Genesis config. So when your blockchain launch, and it's gonna have its own ID, and we gonna like reserve that ID later, that unique identifier of the parachain later on the relay chain as well. Yeah, and that's pretty much like everything like about the Cumulus. I think the Cumulus is not hard, and it's just basically an additional layer on top of substrate that allow you to convert your substrate to the parachain. And that's also like the end of today's sections, and see you in the next video about like repair local relay chain and also like connect our collator node to a local relay chain, so that we have like our parachain fully set up. Then we also like introduce about the tool ZombieNet and also like PopCY.